This lecture will explain about Fourier series analysis, but before that I want to let you know that what is transforms, because it is very important why we are taking Fourier series, what's the meaning of that. To understand that one, we need to know transform first. So here is the start. Linear combination of basis signals. At this moment, just refer this basis signals. You already know that, but I didn't explain that yet. But at this moment, just accept that there is some special signals that exist. So linear combination of basis signals can construct a lot of different signals. And finite energy and finite power signal. So finite means integrable signals can be decomposed. So at here, the combination can be explained by the summation or integrations. So that is hidden here. So integration or summation should be possible to have some finite energy or finite power. The keyword is finite. So that means integrable or summable can be decomposed into the sum of integration of basic functions. So here it says the same things. The first statement says that the linear combination of basis signal can construct any kind of useful signal. The second term, if integration sum over is possible, it is explained finite energy or finite power signal. So this signal can be decomposed by the sum or integration of basic functions. So this one is a forward transform or reverse transform that is explained here. So later on, you may refer to this statement, what's the meaning of this one. So one is the transformation, the other one is the inverse transform. Okay, I would like to let you know that the basics of the transformation, especially for signal processings. So here is a complex exponential basis function, xt. So here is a repeated basis function, okay. Exponential function is very special because it is eigenfunction. It is solution of LTI system. S is complex number, so e to the st can be expressed by e to the alpha t times e to the j beta t. So we know that this is sinusoidal. This one is decaying functions. So that product seems like this one. Exponential changing, that's this curve, but this one is alternating. This kind of sinusoidal. So sum of this one, if alpha equals to 0, then this becomes 1. In that case, just the sinusoidal. Okay? Alpha equals to 0 cases, it is just the sinusoidal signals. So you may have some idea about what is the exponential, especially for the complex exponential basic functions. Okay, xt is this one, and we know that the output of a system, here is a system, is represented by the impulse response, and we applied xt. This is the input, and we would like to measure the output yt. We know that the convolutional equation will give the output response. So here shows that the convolutional equations. Okay, h tau times xt minus tau, taking integration tau from whole range. Then this is just the convolution of that. So this is the output. And we would like to testing this system with the complex exponential signals. So xt is complex exponential signals. Okay, this is it. Then, by taking convolution, x argument is t minus tau. That is replaced this t. Okay, xt is replaced by this one. Then the equation will be looks like this one. At here, we are taking integration with respect to tau. So t is constant. So we can factorize these terms like that. And then later is just the integrations. At this moment, you don't need to you don't need to integration of this one, but this has some special name. This is called Laplace transform, this part. We call that is Laplace transform. So now, if we applied e to the st, this is e to the st, then what is this hs? Hs defined by these integrations. We call this one is Laplace transforms. Just the producting, this is input xt, so this one can be expressed like that, s times xt. So we assume that the xt is exponential functions. By use of Laplace transforms, we can express the output very simply, just the product of that. So this is the Laplace transforms. And then the another one in discrete domain. This one is continuous domain. Discrete domain is the same. This is impulse response. We taking the input as an exponential function. Xn is the same as e to the Sn. So here T0 means the sampling. You know that here is xt. Xn means it is a sampled version. So this is discrete time. So sampling occurred over the time domain. The time difference in discrete time domain, if there is some continuous signals that exist here, xt, then we just sample that one with specific time. So this one like that. And periodically we sample the input signals. Okay, so this is the input samples, but the time difference of sample to sample we call the sampling period. That's the T0. That's shown here. T0. T0 times n is actual time. So it's the same, just the sample the exponential function. Okay, and here e to the s times T0 is defined by the g. Then we can define the xn looks like this one. You know that this is g, so xn is g to the n. So this part is g. Then in discrete time domain, the convolution are given like these summations. Okay, so at here we just replaced xn minus k with gn minus k, but this one summed over the k variable, so g to the n is constant, so this one is actually input signals xn. Okay, by taking sum this one with producting g to the minus k, that is similar to this integration in continuous version. So this part is defined as g transforms, so g to the n. So this one is input. So because of the similar reason, we can make it simple, the system response, by use of these functions. This one is xn. This one is input, but the requirement is the input should be complex exponential function. So if input is complex exponential function, it's quite easy to solve the system. Okay, but in actually xt usually not the complex exponential function. But if we can decompose some input signal into a sum of these exponential signals, then we can separately calculate it due to the LTI system by use of superposition theory. Due to this exponential function, we can find out the one, and the second component can be given like that, last component given like that. So output response is easy to compare to convolution. We didn't use the convolution, but if we know that the transform functions, then we can easily find out the output response. So there is two statements required. The first one, input should be decomposed into the sum of complex exponential functions. Okay. If it is possible, then we can rely on these equations. Okay, that's the whole story for the transformations. So, to utilize that kind of transformations, the first requirement, input should be decomposed into these summations. So, in discrete version is the same. Input sequence decomposed into sum of scaled exponential functions is the, if it is possible, then y output can be calculated by this equation, not rely on the convolution. You know what, the convolution has a lot of complex multiplication and addition is required, so the hardware is very large, bulky. But you know what, this is quite simple equations compared to the convolution. Okay. Okay, here shows that there's some basic definitions for the transformations. Okay. First one is a basis function are defined three different ones, but I said that all these one are exponential, complex exponential function. This one is general one. HS we defined by this product and taking integration. With this transform is called Laplace transform. So HT transform to HS. There is a Laplace transform. I said that if S, you know that S is a complex number, okay? If S is alpha plus J beta, then e to the minus st are equals to e to the minus alpha t times e to the minus j beta t. Okay. This one is the exponential decaying function. This one is a sinusoidal one. If alpha goes to the 0, then this becomes a unit. Then it becomes this one. That is called the Fourier transform. So Laplace transform and Fourier transform shows that the similar expression, just to change the basis functions. In case of discrete domain, we defined G as e to the s to the t0. Okay. Then you may understand what's the similarity between these two things. T0 corresponding to sampling time. Okay. So this is called the G transform. In this lecture, we are using these three transformations. Okay. From here, we talk about the whole syllabus shows that our schedule. Fourier series, Fourier transform, and then move on to the Laplace transform, and lastly we refer to the G transform. All those things are explained in these tables. Okay. But at here, some